All right, this is the third part of the lecture, and actually the last one from the Hadron structure experiment. In the previous lecture, we talked about the some of the results from the unpolarized fixed target measurement that proved the more larger X focused over. And one of the things that we discussed was the structure function ratio between neutron and proton. That you can extract the ratio between the d quark and u quark. And we talked about this observer has really large uncertainty when you go really large X limit, right? And we also talked about some of the measurement that can actually improve that. And one of the reasons that there was difficult was because our neutron target is not actually free neutron target. And then therefore we consider a different approach that to reduce the model dependent of when you extract the active neutron from the active neutron, for example, right? So that's one thing we discussed here. The other one we discussed was about the C-quark flavor asymmetry. So we looked at the D over U ratio at large X region, and then we looked at how about the C-quark ratio then, right? And the measurement that we extracted this C-quark ratio was using the Drell-Yang process, right? So everybody remember what the Drell-Yang process was? Everybody remember? Yep. You have one quark from one hadron, and then anti-quark from the other hadron, right? So therefore, it will have a sensitivity to the anti-quark there. So the extracted signal, initially the measurement shows this the abandoned d bar u bar ratio being above 1, that you have more abandoned d bar quark in certain X region. But on the other hand, this down slope in the much larger X region required more high precision data, and therefore we got it here. So the new data was showing that indeed there is the flavor asymmetry in unpolarized light anti-quark C in the X region around up to 0.5 or so. And then if you look at the data here, this one seems sort of a flat that doesn't come down. But if you actually do the analysis for much larger X region, eventually we expect to be this one goes down naturally to close to 1 for the anti-quark. The very large X region, you not expect those to be still asymmetric. So and then we move on to the polarized proton structure, and we start looking at the longitudinally polarized proton structure, or we call the helicity distribution. And one of the issues that we had was that if we've been relying on the DIS, which is really good proof for looking at the internal structure of the proton, but has a limitation when it comes to the polarization because you can't access the gluon directly, and we don't have enough data, right? If we have enough polarized DIS data, like we had for the unpolarized case, then we could improve this one much better. But in the meantime, what we did was that we look at the process that actually has direct sensitivity to the gluon, which used the proton-proton collision, internally polarized proton-proton collision, and looking at the asymmetry from there. And this shows the actually projection of the first moment of the gluon helicity here as a function of minimum x. And in here, when you look at this very light color of the error bar here, that's when you only have DIS and semi-inclusive DIS data only. And once you add the rig data, and you have this much more reduced, yet here in the large X region, it has large uncertainty, but still in the region where the rig data is actually sensitive, you can see the uncertainty reduction here from this here to in here, right? So by adding the rig data where the data is very sensitive, this region, the uncertainty reduced a lot from here to here. And ultimately, we expect to have polarized DIS data from the EIC. And remember the gluon structure function mapping, when you have EIC, it expand the XQ coverage a lot compared to our current data. And if you include this data, then you can see that the reduction of the uncertainty here in the much darker error bar here, okay, in the small X region. All right, the last one that we talked about before the end of the first lecture was about the polarized C asymmetry. So since we talked about the unpolarized light antiquarks, C has this asymmetry that have more D bar than U bar. How about the polarized case? And for this, we look at the process of the double production in PP collision, which is because of the periviolation nature. It actually has information about the quark flavor, then therefore you can separate it. And from that, we look at the data, and the RIC data where it's sensitive around intermediate X region around 0.15 or so. That's where you have a most uncertainty reduction here, for example. And not only that, that you also have this clear showing that there is polarized identical C asymmetry as well. But in this case, you have more polarized U bar quark than polarized D bar quark, which is the opposite compared to the unpolarized case, right? But have almost somewhat similar. All right, so this is the now third part of lecture. So far as we discussed about the one-dimensional polarized structure of the proton, we are now going to move on to the 3D structure, since as we try to understand more deeper about the proton structure, now we realize that we do really need a more full picture. And as you have been hearing from the previous lecture, there is two types of measurement. One is the TMD measurement, and the other one is the GPD measurement. So we'll discuss about some of the recent results from this TMD and GPD. And then we will conclude by looking at what other opportunities are before we have EIC. All right, so as we mentioned, the collinear PDF that we look at so far is the unpolarized pattern distribution functions, and then helicity when you have a longitudinally polarized proton. And then there's another third one, which you already heard about it, which is called transversity, which is the transversity when the proton is transversely polarized, and the difference between the number of the quark polarization, which is parent to the antiparallel to this transverse polarization of the proton, okay? And that's called transversity PDF. So we'll revisit this one in the later part. So now we are moving on to from the one-dimensional to the multi-dimensional structure of the proton. To know the entire knowledge about the structure of the proton, you actually need to so-called this Wigner distributions, which is this five-dimensional distribution that you have X and transverse momentum and then transverse position, right? But this is so far is not you can measure experimentally, although there has been some suggestion about the observable from the theoretical colleagues. So what we are actually doing is looking at this in transverse momentum perspective or transverse position perspective. So if you integrate over the transverse position, you will get to this X and KT dependent distribution, which is called transverse momentum dependent distribution. You have this transverse momentum come here. The other one is you have X and transverse position dependent. This is called generalized pattern distribution function. If you further integrate over this information about transverse momentum, then you get to this collinear pattern distribution function. Okay? The GPD, if you integrate over the Bjorken X variable, you have information about the form factor. So let's talk about the TMD first. So we already actually had a series of the lecture about the TMD given by Andrea, really not good lectures there. So we won't discuss further anything detail about then what he discussed, which I don't think can. But we will still talk about some of the basic stuff here. So for the TMDs, at leading twist, we have total 8 distribution function, Parton distribution function, and also the fragmentation functions. And depending on the polarization of the quark and target, then you can have actually different TMD functions. And if you look at this diagonal part here, actually, you may recognize some of the familiar names here. This one here, unpolarized, and both unpolarized, is the just unpolarized one-dimensional Parton distribution functions. When it's longitudinally polarized, both, it's helixity distribution function, right? And similarly for the transversely here. So when we talk about the TMD and about the off-triangular momentum contribution to the total proton spin, there's not quite direct link to the off-triangular momentum from all these TMD functions, unless some of them with model dependent. But still, this one tells you that it has connection to the off-triangular momentum, because all this off-diagonal part, which means if you don't consider the Parton's transverse motion, then they will be all vanished, and only you will have this collinear part. Okay, so there is connection or link to the off-triangular momentum from this Parton transverse motion. So there are several channels that you can actually access the TMD experimentally. In here, that's what we are interested to look at more observers. One is the semi-inclusive DIS, and also the Joule-Yang or W productions, E plus E minus, or from the PP collisions. And having this all different process, again, similar to the unpolarized case, really give you a chance to actually test how the factorization and the concept of universality works. So this is the overview of the program of the TMDs in the current data and in X and Q square phase space. As you can see here, there's here at the right bottom corner, again, this is from the fixed target experiment from the data of 12 GeV. A little bit higher energy fixed target experiment from the Compass and Hermes here. And then there is this PP collider from the Brookhaven, the rig from the STAR collaboration, where it measured the W. When we measure TMD observables, the most convenient channel is semi-inclusive DIS. And you probably talk about this already, because the semi-inclusive process is really ideal, because in this cross-section of the semi-inclusive DIS, you naturally have this all this reading twist TMD appear with corresponding this azimuthal dependence. And when you talk about this non-collinear, so when you have a collinear Parton distribution function, you only depend on X, right? And in this case, to look at this, you only need the 1 Hz scale. For the TMD to be applicable to apply for your observable, you need actually 2 scales. One is 1 Hz scale, one is the other soft scale, and that is related to the Parton's transverse momentum. In this case, the Hadron momentum that you measure will be the soft scale here. So if you can see here, there are different structure function with a different polarization of the beam and target. And when we actually do the measurement, for example, if your beam is unpolarized and target is unpolarized, and what we measure is so-called target single signal asymmetry. So you have a beam unpolarized, target polarized, collision happen, and measuring the certain final state hadron that you want, and then count those number of hadrons, and then when the spin is up and down for the target polarization, and that's your asymmetry. But this asymmetry is not just one particular TMD asymmetry, but it's actually a combination of asymmetry that all have this unpolarized and polarized, transfer polarized structure function term here. So for the target single signal asymmetry, you have this Collins asymmetry term with its corresponding azimuthal modulation, and then Sievers and fresh velocity here. Okay, so this is what you measure, and in order to extract this Sievers, Collins, and fresh velocity asymmetry, what we do is that we perform so-called Fourier amplitude analysis. Then you can look at this one individually there. Okay. So let's look at some of the results. Some of them were already introduced, but let's look at this together. So first, for the Sievers function, you might have talked about this, how the Sievers function and Collins fermentation function got much more attention and studies at the beginning when people start looking at the more transverse momentum dependent functions. So the Sievers function and other TMD variable in semi-excluded DIS has been really well studied by Hermes and Compass. And this is one of the Hermes results showing this the Sievers amplitude as a function of the x and z and transverse momentum variable and in one-dimensional. So the rest of the variable for this is then integrated over whenever you look at this in one-dimensional dependent. And this is showing this pi plus and k plus different final states, Hadron states. And you can see in general both first, in these asymmetries are non-zero. So, and also quite large. So it's showing clearly that there's non-zero U-quark Sievers for the U-quarks. And what we really want to know about when you look at the TMD is that you want to have more information, then you really need to bin this asymmetry in multi-dimensional phase space like this. So you need to do this multi-binning the presentation of the data. It means you need to have enough statistics to do that. And Hermes has the analysis recently and then published their reanalysis result here in this 2020 paper. And this is their three-dimensional binning of the Sievers asymmetry analysis for the pi plus as an example here. And it was also measured by Compass experiment as well. And here it shows the Sievers asymmetry here as a function of one-dimensional variable x and z and bt. And also compare with the Hermes, and you can see that those two values are pretty similar. But one thing to note that here is that you have the Hermes and Compass a little bit different, the Q-square, not little bit actually, a bit of different Q-square value. So if there is TMD evolution effect, and when you have a quite different Q-square kinematics between two results, and if they have a difference a lot, then that may indicate that there is TMD evolution effect. Okay, so there is a thing that to look at when you compare the data between different Q-square. Okay. And when you look at this in the Z here a little bit more closely, and in this the asymmetry, there's a little bit of difference between Hermes and Compass. This maybe indicate there's evolution effect, but the order error bar for the points are still large. So we'll see. And about the Sievers, how it also had a lot of more attention than out of the other TMDs, it also led to the universality. So yesterday you had a dedicated lecture about this, discussing about the modified universality of the Sievers function, right? So, and it can be compared between the CDs and then the dual-Yang or G process, and you expect this sign change here. And this one is the Compass dual-Yang measurement, and they also do the measurement with the CDs as well. And that's actually really nice feature that if you have two measurements with the same experimental setup in the same facility, then you can compare them, and a lot of the common systematic effect can be canceled out when you compare. So here, it compared the asymmetry with the scenario that there is sign change and no sign change. And you can see that with this data agree with the sign change scenario here. the W measurement from the PP collision with the star. In this case, you have this the W plus and W minus charge, the plus here and minus charge, and then the asymmetry measured here as a function of the rapidity. And then compare with this scenario again when there is sign change and no sign change. And you can see that here, when there's no sign change, when there's a sign, this is all comparing with the sign change scenario with the non-zero asymmetry here. So you can see that they have, they favor the sign change scenario as well. On the other hand, about the evolution effect, when you compare with evolution or non-evolution, but if there is evolution effect there, then asymmetry will be very small value here. But the uncertainty for TMD evolution included the prediction is pretty large. So there'll be more of a statistics for this data. So hopefully this uncertainty will be reduced and then we'll be able to see a little bit better. All right. The other asymmetry that's important in the TMD that has been studied quite a bit is the Collins asymmetry. So this Collins asymmetry related to the final state effects. And what you extract is these Collins fragmentation functions. This is the Hermes result for the pi plus. And again, this is one-dimensional analysis. You can see this non-zero asymmetry here, and then different sign for the pi minus. And then on the right-hand side, this shows this, again, the three-dimensional binning analysis for the same observables. And the Collins asymmetry can also be measured from the PP collisions. Again, remember when you look at this TMD measurement, you need two scale. So if you think about any inclusive measurement from the PP, you can quite have the TMD applicable there. But like W, that you have the hard scale naturally set by the W mass, for example, then you can have two scales there. But for the pion production, if it's inclusive, you need another. But luckily, if you look at the pion production within jets, then you can extract the Collins asymmetry here. And this is one of the results that was published a few years ago. And it's function of Z here for the pi plus and pi minus, and compare with the different theory calculation here. And this shows there is Collins asymmetry measurement can be happening in proton-proton collision for the first time. And when you compare this with the model that's based on the cities or the plus and minus data, and you can also check this universality of the respect of QCD. And those calculations overall agree well, except for this sign here a little bit. And there is a projection for the further data that expect for this measurement with the reduced uncertainty there. So next TMD function that we want to talk about is the transversity. Remember, the transversity is one of the also third collinear pattern distribution functions. But it was least known because it's not really easy to measure. So you've been discussing about this chiral nature of the transversity functions, right? So if you want to measure this, you need to combine this with another chiral object or observables. So you can do that by looking at this Collins asymmetry, for example. Then you have a transversity and then Collins fragmentation function. And so then you can extract the transversity there. You can also do that from the other, for example, interference fragmentation functions from the plus and minus, or also from the PP. The important thing of the transversity, not besides that it tells you about the transversity polarized distribution of the parton in collinear picture, is about the tensor charge. So the tensor charge is the fundamental quantity of the nucleon, and is also the lowest moment of this transversity here, as defined here. And as it is being a fundamental quantity of nucleon, it can be calculated by lattice QCD using the first principle. And you can compare, is it covered here, the values with the lattice QCD there. There was a comparison plot. I apologize that. I will fix the slide later. And this plot that I show here is actually then one of the projection of the future experiment, and showing that how this future high luminosity fixed target experiment can improve this uncertainty of the transversity in the large X region. It shows this transversity for the comparing before and after, including the this new data for the U and D quarks. The U is the red one, and then D quark is the blue here. You can see this very darker, much darker central line here. That's how much is being reduced there when adding this new data. Okay. And this data is coming from the data of 12 GeV. Another TMD that, besides these Sivas and Collins, I want to mention is the Vermilder TMD that you can actually measure when you look at the dual Yang. So remember, you have dual Yang observable to look at the Sivas asymmetries. You can also look at some unpolarized TMD distribution function. One is the Vermilder here. So you can measure this using from the compass, which is applying this dual Yang. You can also measure this from the other future experiments, so-called CCAS, which is the foreign-use dual Yang. And the other one that you can also measure is the Vermilder, obviously the semi-inclusive DIS, that you can extract all these 8 ring twist TMDs there from the series. This is one of the results from the compass collaboration. And you can see here there is, when you look at the asymmetry, for the as a function of X or G and PT here, for the positive and negative hadron here, there's clear signals and kinematic dependence showing here. All right, so far what we discussed was the transverse momentum dependent functions. But I also want to talk about higher twist functions. So you talked about this difference between the ring twist and higher twist from the TMD lectures, and you actually saw this plot together during the lectures here. This was showing this transverse synchronous asymmetry in PP collisions back in 1970, and they measured really large asymmetry first in the argon, and then they measured different energy at Brookhaven and Fermi-Lab and RIG. And they continue seeing this very large asymmetry, and looks like the size of asymmetry is almost similar, even though you're increasing the energy quite a bit. So it was quite puzzling, and people started thinking about what is really causing this or origin of this transverse synchronous asymmetry, and then come up with this the transverse momentum dependent effects, interspace effects, or final state effects, and so on. But in fact, most of these PP observables, they are actually collinear observable, and you can study those inclusive hadron measurement from the PP for the transverse synchronous asymmetry in terms of the twist multi-pattern correlations in collinear framework. So here, as being a collinear observable, you just need 1 Hz scale, so therefore you have an inclusive hadron measurement there. And with a high PT, and so therefore it's relevant for most of them. And there is a contribution in the asymmetry that you can consider. Either this is from the quark-gluon-quark correlation contribution, or the tri-gluon correlation function contributions. And this RIG measurement, most of the observable, you actually expect this quark-gluon-quark contribution to be pretty small. And most of the measurement that I'm going to talk about is actually more sensitive to only the tri-gluon correlation functions. All right, so I have 2 measurements here that are sensitive to the tri-gluon correlation functions. One is the direct photon measurement from the PP collision, and proton is again transversely polarized. And this is actually the first measurement of the direct photon transverse asymmetry that is published here. So here what we see is the transverse asymmetry of the direct photon production in PP as a function of PT, and compare with this theory calculation that predict the asymmetry. And you can see here this green curve is this from the quark-gluon-quark contribution, which is very small here to 0. And the other, this blue and red one, is the trigluon contribution, assuming some different model in the calculation. And if you look at this, the data in like around 5 GB or so, and these data actually have a bit of statistical power. They can constrain this the model better than currently what you are seeing here. And the other measurement is this pi zero production. And the pi zero compared to the photon production has both initial state and final state effects when you look at it because of the hadronization in the final state. And we measure this at the mid rapidity, which means around the more central region of the detector instead of the forward region. Both are in the mid rapidity measurement. These measurements are sensitive to the gluon contributions. And when you look at the pi zero measurement here, we see the asymmetry is constant with 0, but you can see the precision of the data points in the lower PT region here is quite impressive here, okay? So this is a very high precision data that can also contribute to constrain the trigluon correlation function. All right, so we've been talking about the transverse single signal asymmetry in PP collision. But we also took the data in PA collision when proton is polarized for the first time. And what's this PA collision give you when you measure this asymmetry in this PA collision compared to the PP, you can then how this extra nuclear environment is affecting to your asymmetry measurement, and then study the nuclear effects in the asymmetry. One of the interesting measures that we have is charge hadron asymmetry that we measured a couple of years ago. What you're seeing here is azimuthal modulation of the asymmetry as a function of phi here. When proton-proton collision produce the positive charged hadrons, it's an unidentified charge hadron, compared to P aluminum and P gold. And what you're seeing here, how the asymmetry changed from PP to P gold. You can see that it's suppressed in the P gold collisions, right, compared to PP. So this was quite interesting, and there was in fact some discussion and prediction from the theoretical colleagues that for the nuclear environment, in PA collision, for example, there could be some suppression of the asymmetry in PA because of this saturation effect. And that would be A10-13 of suppression. So we compare that with this fit of this our asymmetry as function of this the A dependence, and extract this the order, and it does say that it does indicate that it obviously disfavor of non-A dependence, and looks like the value of this is quite similar to the A of 1/3 of a dependence here. This alpha value here is this what we optimize here. Okay, close to 1 means it has this dependence, right? One thing I need to mention is that the measurement happened here is actually not in the saturation region. So this is quite interesting because we still see this strong suppression of this asymmetry in P gold, while we are outside of the saturation region in terms of in our measurement kinematics. And on the other hand, for the observer at the mid rapidity, we didn't see a dependence, anything strong. But this one was done in forward rapidity. So this would be an interesting measurement to have a little bit better precision at the rig with the new detector that will take data in PP collisions. All right, so we so far talked about the transverse spin physics. Let's move on to the generalized Parton distribution functions. So again, you have a good lecture given by Barbara about the GPD from the theoretical point of view. So I won't go through much about the introduction here because you've been already given But basically, what you have this with GPD and TMD, you can have this the nucleon tomography and have this three-dimensional imaging of the nucleon structure. For the GPD, there are 8 leading GPD. 4 of them is chiral even, 4 of them is a chiral odd. And the other thing important is that the Kirk orbital angular momentum contribution to the proton has this connection with these GPD functions. So to study this the GPD, we measure exclusive process, differently virtual Compton scattering, or differently virtual measurement production, or time-like Compton scattering. So what we measure is a cross-section and some other asymmetry, like we change the beam charge, or the beam spin, or single spin asymmetry. Okay, and depending on your asymmetry, you can actually see what kind of amplitude or is more sensitive to the certain GPD, like this. I should mention also, actually, then from the measurement, what you're looking at is not directly GPD, but it's the Compton form factors. Okay, you can directly access the GPD from the measurement. All right, so GPD program, you have in the collider mode in HERA, actually. So HERA and H1 NGOs had the EP collider. The proton was unpolarized. So there is, but the electron beam, you can have different charge, for example, and different spin. So they have measured some of the cross-section and or the beam charge asymmetry there. For the fixed target, we have Hermes experiment. And with this sharing this electron beam from the HERA, it can have this beam charge and beam spin asymmetry, as well as the target is also polarized. And it also went through some upgrade throughout the year to have the recoil detector. And we'll talk about the importance of the recoil detector later. The other experiment is at the JLab, is in HOR A and class, that measure the some of the GPD observers there. And for the HOR A, it doesn't have a recoil detector, so it has to use some different technique to reconstruct the kinematics. On the other hand, class has the full event reconstruction capability. And the last but not least is the COMPASS experiment, has this polarized muon beams with a different charge. And so you can have the different beam charge or beam spin asymmetry as well as a cross-section and single spin asymmetry. And polarized target there with a recoil detector. Okay. So as I mentioned, that there are different processes to look at it, but we will mostly look at the result from the DBCS process, which is the most well studied and measured so far. And this shows the current DBCS data in where their kinematics are covering in terms of X and Q scale. And here on this side is the data fixed target, and then this region is by the compass. And then those higher Q scale and then low X region here is by the H1 NGUs from the early days. So the DBCS cross-section, when you actually do the measurement, so you're looking at the, for example, electron proton, and then you're looking at the electron and then proton and photon produced, right? But it doesn't mean that this is all coming from this deeply virtual Compton scattering process. There's also other processes, and most of the time it's dominant actually, is Bethe-Heidler process here. So depending on your energy at Q scale, for example, HERA, you may have somewhat similar cross-section between the DBCS and Bethe-Heidler effect, the contribution. But for the fixed target, normally this is actually dominant. So when you look at this then cross-section measurement, for the differential cross-section measurement, you will have this contribution from this DBCS alone, and also the Bethe-Heidler and also interference term. And you can sort of try to isolate by looking at it. And for the GPD or Compton form factor, you can actually linearly look at it from this interference term here. All right. So one of the recent measure was from the COMPAS. COMPAS has this measurement for the different all sorts of charge or symmetry or the beam spin symmetry. So more earlier days data as well and different data as well. But I just want to have this one recent plot these days have in here from the cross-section measurement. This shows this t-dependence of the cross-section. When you have this differential cross-section for here, you can integrate over, for example, the azimuthal angle, and then look at the slope of the cross-section, depending on the t value here. And when you look at the slope of the cross-section with respect to the t, you can extract this slope parameter here. This is shown in the capital B. And this slope, t-slope of the cross-section is actually related to the distance between the quark, that's the stroke quark, and then the spectator. And then you can actually then extract this here from these slope parameters. This shows this t-slope parameter as function of the direction x from different experiments. So this blue points are from the Hera, and green is Zeus, and then this red one is from the COMPAS. And you can see that then, and they have a little bit different Q-square value, and there's a curve for the different Q-square there from different models here to compare. Next, we look at the data from the JDAP. So for the fixed target overall, you have a pretty reasonable rate if you have a solid target, for example. But JDAP really has this high intensity electron beam, so it has a really good advantage of the luminosity. So you can have the fairly precision data from JDAP, and here is some of the results that come out from the JDAP core A, looking at this the cross-section measurement from the DVCS process. And what you do is that you have a different contribution that DVCS contribution and also the Beyer-Heidler contribution. Then by doing the fit, then you can actually separate them here. So for example, this the red one is the DVCS, the contribution extracted here, and then green one is the Beyer-Heidler contribution here. And we talk about this at the lower Q-square region. Those are more dominant contributions. From this, then you can extract the Compton form factors. And this is showing this 4 different helixically conserving Compton form factor here. And you can also do the measurement for not only the proton target, but also for the neutron target. So the measurement was done for the neutron target, and you can then do the flavor separation of the Compton form factor by combining the data with the proton target data. And this data is actually then sensitive to the GPDE part. And here it shows this the extracted the Compton form factor from the neutron data from the 6GeV here. So we've been looking at the data and sort of assume that we have these good exclusive events that identified, right? But when you do that exclusive measurement, it's pretty tough to do. Not only that, you have to have very strict requirement for the experimental setup to detect or the scattering process produced particles. And you also need to then make sure that your data is exclusive event. And so how do we actually tell that this is exclusive event? So to check the exclusivity, for example, let's look at the DVCS here. The DVCS is from the E plus P, and then you have the E and proton here after scattering, and also the photon here. So you can normally measure this scattering electron and photon from the detector. But in fixed target, actually, you only have this electron beam has energy coming in, but your target is at the rest, right? So after the collision, your proton targets, the recoiled proton, where do you think it's gonna go? For the collider, when both beam is colliding, and normally in the proton beam has higher energy, and your proton recoil will just continue straight close to the beam line, right? And that's what you can do in, for example, Hera. So for the collider setup, you can have this, for example, this is one of the event displays showing the example events of the EP to E gamma and P events. And you have this here, electron produced, and then photon produced here in the colorimeter, and the photon detected at the colorimeter, and electron detected at the colorimeter. And then where the proton goes, it just goes this down the beamline. Okay? So then you can have this very forward tagging detector to tag this recoil proton. Okay? And you can have the full reconstruction of the events. And then for the fixed target, as we mentioned, but now target is at rest, you only have electron beam, then target recoil will be pretty slow, right? So, but all your detector normally in the fixed target is in the front region, right? It's asymmetric collisions. But you want to measure this, if you want to measure this recoil proton, one thing you can do is, for example, you can have this recoil detector right around at the target region. Okay, so this is recoil detector that COMPASS had, and this is where the target chamber is. But what if you don't have recoil detector at all in the fixed target? What can you do? You can do still missing mass reconstruction, right? So you detect scalar electron and photon, and you know the beam energy, and target was at rest. So only thing you don't know then, this one, right? You can then reconstruct from whatever you know to the unknown, because it has to be conserved, the momentums. So here, the strategy in the whole AAD-VCS experiments happen is that you have the beam coming in, and you have a target here. Your scalar electron is measured by one of the spectrometer here. And then your photon will be detected by the electromagnetic colorimeter here, right? And you can see the difference between the setup here. You have this spectrometer, detector package, pretty complicated spectrometer here to detect the scalar electron, right? But on the other hand, to the photon detector, just colorimeter sitting there, right? Can you tell me why you have this different type of setup here in here? When you're detecting electron and you're detecting the photon, what's the difference? Charge difference, right? So when you want to measure the momentum really well of the charged particle, what you need is a spectrometer, right? And that's why you have this whole series of magnet, and then detector package at the end of this spectral magnet, so that you have a good energy selection of the energy, the momentum of the electron from your spectrometer, and then detect it here. On the other hand, the photon is a neutral particle. You just need to measure the energy, right? So you have a colorimeter here. This is the reconstructed missing mass square distribution. And you can see this black one is from when you count all the events, like you have a data, and then black one is you have everything, whatever you have, okay? It already has some of this missing mass peak here, right? But you can further reduce this. Part of the contribution for the photon is actually coming from pions, because pion decay into photons, right? So pion background, whenever you do some single photon or direct photon measurement, is your major background contributor, okay? So you can then reject the pion. How do you reject the pion? How would you reject the pions when you want to just look at this direct photon event? Anyone? Any suggestion? What do I do? I'm not going to be doomed here. I have so much background here. Any suggestion how you want to get rid of the pion background? This is a pi zero that we're talking about. Say it again? Invariant mass. Very good. Can you explain a little bit more what you do with the invariant mass? How are you going to reconstruct it? Okay, so basically calculate the invariant mass of these two photons, and if it's same as invariant mass of the pion, then you can say those two photons are coming from pion, right? Very good. So that's how you can actually get rid of it. So here, this green histogram is a pion decay contribution. After you remove it, this circle point is what you have. And you can compare this with the Monte Carlo, and you can set where you want to cut the missing mass cut here, like this. Okay? So yeah, so we just already talked about this, that how to measure the pi zero. The reason why I actually asked you about it is that pi zero is really quite important hadron that in the particle physics here. This is, I would call the VIV as its own observable, or should I say VIO, because it's observable. But for its own measurement, for example, if you look at some other asymmetry that we talked about it, whatever you look at as a signal out of all the other hadrons, normally it's pi zero. It's such a, also good for the detector calibration because of reason that we just talked about it, because of well-known the mass of the pion, and also the decay mode is almost primarily to the 2 photons. So I was about to actually give you this as the something to work out together, but we did. So let's just review this. So the pion decay very quickly, right? And the decay mode is mainly 2 photon decay, like 98%, 99%. The other is the Dulles decay, which you have one of the photon decaying to the electrons internally already. So you have a 1 photon and electron and positron pair. Okay, that's the Dulles decay here. So we already talked about how you detect the pion by reconstructing this from the 2 photon decay. What kind of detector would you have then? To detect the decay from the pion. What kind of detector? What are you actually measuring? So what do you have to detect? It's the photon that decayed, right? So to detect the photon, what kind of detector would you use? Yes, colorimeter. Very good. So it's the same colorimeter you have there that you measure your signal photon, and within that signal photon what you have, there is background photon there basically, really, right? So, and the third question, would you detect pions? We already answered this by missing this invariant mass reconstruction. So you can calculate the invariant mass in terms of 2 particle collisions and 2-body decay. And for the massless, it gets quite simple here, right? For the photon, you can base it then here. And for the collider, you can also reconstruct the invariant mass from the variable of the angle, right? The pseudo rapidity and then the azimuthal angle difference between 2 photons. Then this is one of the examples that reconstructed the invariant mass of the 2 photons. And you can see the peak is around here. And this value should be around pion mass. Which one? How much? Yeah, around 135. That's 135, okay? So if this is not around the 135, then you can use it actually for calibration, as I mentioned before. It's very common to use the pion as your energy calibrator. If you have a colorimeter, then you can use the pion to calibrate the constant for the energy, like gain constant and so on. Because you know where its peak is supposed to be, if it's off, then when you convert your signal into the energy unit and calculate the energy, how much energy deposited in your colorimeter is off, right? So you can use that to calibrate detector as well. So such a good particle, right? It's such a good measurement as it is, good for calibration, easy to reject as a background as well, all right? And the other way to ensure the exclusivity, as I mentioned, is just doing the full reconstruction. To do that, you actually need to have a really good detector system. This is one of the class experiment that JDAB, again, is doing it. And they have a quite good detector package of multiple system. So you can have electron detector system, and also the photon detector system, and also proton detector system there. And you can measure them all and reconstruct this the mass and also the angle there over here. from the full kinematic construction. Okay, we're almost there. So we so far talk about the result and measurement that happen or happening from all around other factory experiments. And here I just also want to point you, because you guys are mostly students, and moving forward, what you would be more excited is that what's going to happen more, right? What kind of new data I will get, or what kind of new observable or the new physics that I can look at it. So here is some of the experiments that are relevant to the hadron structure experiments for the future data, but most of them are actually already continuously taking data. And again, in the end, there's the EIC over here. So some of them I want to point you, in case you're not familiar, is the S-Phoenix detector. This was upgrade or the transition from the previous Phoenix detector at Brookhaven. And this one is mainly for the heavy ion physics, but also has this called QCD program. So take data in polarized proton-proton or proton-ion collisions. And then some of the measurement that we looked at before can be improved quite a lot than before. And the other one is the STAR experiment from Brookhaven again, and they had a forward upgrade, and then has been taking the data from the PP collisions for their core QCD program, and also will take data this PP running as well. And here, this is the forward region, the upgrade here. Okay, and especially this forward region upgrade is good opportunity to study this gluon saturation. Because you need really forward detector for that. All right, third one is upgrade from the compass. So they are, I don't know if it's approved actually, they have been discussing about upgrading the compass, either compass plus or the coordinate amber, for the continual measuring nucleon structure measurement, also some other new measurement. Like hadron mass, more focused hadron mass focused measurement, or also the pion kaon structure and proton radii, and also spectroscopy. And the last one I mentioned is so-called solid. This is a JLab. And JLab, the solid detector, really take advantage of the high luminosity of the electron beam flexibility there, and then has this full detector package here. So when you have the full coverage and large acceptance detector with high luminosity, what you can achieve in terms of parameter or performance, which one is it? What can you achieve if you have a high luminosity beam, large acceptance detector with the full azimuthal coverage? You will have really good range for your data, right? You have a large amount of data. So solid will be able to provide very high precision data for different channel. For example, this 3D structure, we can do multi-dimensional meaning of this TMD asymmetry, for example. We can also look at this, the electroweak physics, and also the J-psi production, and so on, okay? So there is quite a good program for the solid physics there as well. All right, so we are actually timed out, but I just want to briefly go through what we have talked about, okay? So we talked about starting with the basics of the accelerator and the detector from the first day, right? And now, whenever I actually talk to you guys, you can now think about what kind of detector you can use for measurement, and then they will also help you to think about, oh, this measurement was done, but there might be the limitation, and so on, and make you easy to understand the data, even though you're not an experimentalist. I know most of you are not, actually. But understanding your data and systematics is very important when you look at them and study them from the theory perspective as well. Next is that we review some of the measurement of the hadron structure for both unpolarized and polarized, and also one-dimensional and multi-dimensional, and look at some of the important or interesting results from the past few years. So, are you excited about it? New experiments in EIC and so on? With all this listening the theories and about the experiments data that before EIC as well. Interesting physics. Interesting. Oh, then I succeeded. Okay. All right. This is the end of my lecture. Thank you very much for attention.
Sanghwa for a very nice and motivating set of lectures. Questions?
You're more than welcome to come talk to me anytime during the break, which I quite enjoyed and very impressive actually. You guys are very good at actually discussing here. I've never seen a school actually they're doing this so well. So very impressive. But anyway, I'll be here until probably next week. So. Right.
I just have a short comment. COMPASS experiment started taking data last, sorry, not COMPASS, AMBER.
Mm-hmm.
AMBER started taking data last year.
Ah, already?
Already.
Yes. So I wasn't
aware
of it. That was quick. I thought that they proposed like only a few years ago about the upgrade. And I thought that took a while.
They're planning the second run now.
Oh, okay. Well, there we go. Do you know how many years are they going to run? It was
I believe they have been approved for 4 years.
Mm-hmm. So they're in the second year?
Each one of, the second year starts now.
Mm-hmm. Okay.
So, if there are no further questions, let us close this session today.